on refraction, and it follows on for the lessons on reflection, but it stands alone in its own right. Okay, then let's take a simple example of a block of optically dense material. And when I mean optically dense, what I mean here is that it is transparent. You can see through it, unlike something like wood or a metal. And we're looking very simply at light that strikes this wood, strikes this bit of glass at an angle. And when we're talking about that angle, we need to make reference to this dotted line at right angles to the material. And this line we call the normal. So this is the angle that we're interested in here, I, the angle of incidence. And what we're going to do is see what happens when it strikes this material. Remember that it needs to be transparent. And it can be any material, and the material has what we know as something called a refractive index. And the refractive index, which is this letter N, tells you how optically dense it might be. Okay, however, what we have first of all is the ray strikes this boundary between air and this refractive index. And what's likely to happen? Well, let's just remind ourselves what a wave is. This is a ray of light, of course, and the ray of light is really indicating which way the wave is travelling in. These, of course, are wavefronts. Now, as they hit this optically dense material, let's say glass, let's use that as an example, then it's going to start slowing down, and that is the crucial part of refraction, that it slows down as it hits more optically dense material. So if it slows down, you can imagine a car or marching soldiers, and as they hit the material, that part starts to slow. So if I continue the waves normally, they're slowing up, and therefore, if they slow up, we have a change in direction. Okay, and that is the refracted angle. So as it comes in, this part of the nib of the pen strikes material first, and it twists, and then it moves on. So therefore we have a bending effect. So refraction, essentially, and this is the big idea, refraction is caused by a change in speed. So I've got that highlighted. That is the real reason why light bends as it goes to an optically more dense material, because refraction is caused by a change in speed. Just as a quick reminder there, what's the speed of light? C. It's 3 times 10 to the 8 meters per second. And so therefore, we can, if it is a change in speed, we can define the refractive index as the original speed divided by the new speed. In other words, the speed outside the material versus the speed inside the material. Another important point to note. Okie dokie, well, let's have some rules then. Let's make reference to that normal in both cases. And let's say as it hits more optically dense medium, it's bending towards the normal. So let's get what I define as the simple rules. As we move from less dense to more dense, so we go from less dense to more dense, we bend towards the normal. Okay, excellent. What do you think is going to happen at the other side? When the ray of light emerges from this block, all of these wave fronts are now going to start speeding up again. And if they're speeding up again, you have, with reference to the normal, are bending away from the normal, as opposed to bending towards the normal here. So the opposite effect occurs. So let's go from more dense to less dense. It bends away from the normal. Now, that's all well and good, but we need to be able to put some serious numbers to this. So, one little quick reference here as we come back again. Let's think to ourselves of what's happening with our wave equation. If you remember this being our wave equation, whereby the velocity of the wave, speed of the wave, is the frequency times the wavelength. If we're saying that the speed drops as you enter into this optically dense medium, speed drops, the colour does not change, so the frequency remains the same, the wavelength must decrease. So you can see that this has a certain wavelength here, and this has a shorter wavelength as it goes to the optically dense medium. Okay, so that's all the descriptive material done. Now the rules need to get tougher, so we can actually quantify how much bending towards and away from the normal we have. And here are the equations. I will give you the equations, and they should have been sort of worked through in a practical session as well. So let's call these the complex rules. Okay, we go from less dense to more dense. Then we have this relationship: sine of the incident angle divided by sine of the refracted angle is the refractive index. So let's take a look at that again. Sine of the incident angle divided by sine of the refracted angle is equal to that refractive index. That's if you're moving into more dense medium. Let's imagine we're going from more dense to less dense. Then sine I, let's just call it a dash, shall we, divided by sine R dash is 1 over the refractive index. In other words, just bring your eyes back up to here. This is now the incident ray inside, and that's the refracted ray. Dashes implying it's not the same up here. We're talking about the second side. So less dense to more dense, bending towards, it obeys this law. As it bends away, going from more to less dense, it obeys this law here. Okay, we need to put some of those into practice now. And if you think you can do it, feel free to give them a go as well. Okay, we're going to deal with rectangular glass blocks in all cases. Here's the first one. Here's our first large block. We're going to say it is perspex, like a plasticky glass, plastic transparent, and that means a refractive index of 1.5. First of all, what's the velocity of the wave when it enters the glass, assuming that it's come from air? Okay, if you think you can do that, go for it. Otherwise, pause the video. Otherwise, I'll go through it right now. So first of all, the velocity. Well, we know that the ratio of the speed outside in air to the velocity inside is going to equal the refractive index. So if I want to find the velocity, that's going to be c divided by the refractive index. The speed of light is c. Gives me 2 times 10 to the 8 meters per second. So that's the speed that it's going in with. Okay, let's imagine that the ray of light comes in at an angle of 25 degrees. We know it's going to bend towards the normal. So what is the refracted angle? So question 2 is, what is the angle of refraction? If you think you can do it, hit pause. Otherwise, I'll go through the answer right now. Okay, first of all, here's the equation. Sine I over sine R equals n. We need to be able to do some rearranging of this equation. So I hope you can follow what I've done here. Sine R is sine I over n. Therefore, R, sine to the minus 1, inverse sine of sine, the incident angle is 25 degrees, and we've got 1.5 refractive index. And that should give us an angle of 16.4 degrees. Can't do those in my head, I've worked it out before. Fantastic. Now, the next one. Let's try and invert a little bit and imagine that we've got another glass block. But this time we know what angle it's refracted with, 30 degrees. This time, what's the angle of incidence? Perspex, sorry, not glass. Okay, if you think you know, hit pause. Otherwise, here we go with the answer. Okay, the relationship we write down first. I want to find out the incident angle, so let's hopefully be able to follow this rearrangement. Inverse sine of my refractive index 1.5 sine 30 degrees. And that gives us an angle of 48.6 degrees, which makes sense because obviously it's bent towards the normal. This has to be smaller than the incident. Right. Similarly up here, if it's 25 and it's bent towards the normal, this came out to be 16.4 degrees. So it should intuitively make sense to you that it's bent towards the normal. Great, okay then, let's do 2 more. Number 4, let's imagine somebody's taken into a jewellery shop a sample of something transparent, and they want to know whether it's a diamond or not. The refractive index of diamond is about 2.4. It's very, very optically dense, whereas glass is about 1.3. So there's a range of optical densities between those. So what somebody does is they shine light at an angle of 60 degrees, and they discover that it's refracted at an angle of 22 degrees. So the question is this diamond or more likely to be glass? Okay, if you think you know how to work it out, do so, hit pause, otherwise here goes the answer. Right, we know that this is our relationship for our refractive index. So all we need to do is very, very simply put in the figures, and that comes out with 2.3. So this is more likely to be diamond than it is glass. They've got some money going for them there. Okay, and now the final problem is we are going to invert the situation altogether and use our other equation. So now we have water, a refractive index 1.33. Now we have a ray coming from a more optically dense to a less optically dense. So we know it's going to have to, this is our incident, we know it's going to bend away from the normal. That's our refracted angle. And the question simply asks, if the ray is inbound at 15 degrees, what's going to be the refracted angle? If you think you know, bearing in mind that equation will change from what we've usually been using, hit pause. Otherwise, watch the answer right now. Sine I over sine R is now 1 over n because we're moving from more optically dense to less optically dense out to air. So now we want to rearrange to get R. Let's see if we can do this. This moves up, that moves up. So R is inverse sine 1.33 sine 15 degrees. And that gives us an angle of 20.13 degrees. And that makes sense because you're going to be bending away from the normal. The angle is greater, so this is 20.13 degrees. Fantastic. Right.